Welcome to Mathematical Finance. Today we explore duration and convexity, two of the most important concepts in fixed income portfolio management. Imagine you lend money to a friend. They promise to pay you back over 5 years. If someone asks how long it takes to get your money back, you might say 5 years. But because you get some money back earlier, the true average time is less. This is what duration measures. Convexity takes this further by acting as a shock absorber for interest rate changes. Let us dive in and see how these tools protect billions of dollars in the financial markets. Now that we have introduced the topic, let us understand what duration actually is. Duration acts like a financial center of gravity for your loan. If you balance a broom on your finger, the balance point is not at the very end of the handle, but somewhere in the middle where the weight is equal on both sides. Similarly, duration finds the balance point of your cash flows in time. If a bond has a maturity of 5 years but pays high annual interest, its duration will be less than 5 years because those early payments pull the center of gravity closer to today. To calculate this balance point, we use a specific mathematical equation called Macaulay duration. Conceptually, this formula finds the weighted average time until all cash flows are received. The capital D stands for Macaulay duration, measured in years. The capital P is the current market price of the bond. For each time period T, we take the cash flow, discount it by the yield to maturity Y, and multiply it by the time T. We then divide the entire sum by the total bond price. If the yield increases in the economy, the present value of distant cash flows drops, which causes the overall duration to decrease. While measuring time is useful, investors usually care more about risk. This is where modified duration comes in. It is a direct measure of the price sensitivity of a bond to changes in interest rates. Sensitivity means how much the bond's price will jump up or drop down when the economy's interest rates change. There is a fundamental rule of finance. When interest rates rise, existing bond prices fall. Modified duration tells us the exact percentage change in a bond's price for a 1% change in yield, making it the standard risk metric used by bond traders worldwide. This brings us to the practical formula used by traders worldwide to estimate bond price changes. The formula states that the change in price is approximately equal to the negative original price multiplied by the modified duration, multiplied by the change in yield. The modified duration itself is simply the Macaulay duration divided by 1 plus the yield. The negative sign in the formula mathematically enforces the inverse relationship we just discussed. When interest rates go up, the bond price must go down. If the yield increases, the change in yield is positive, resulting in a negative price change. Before we move on, let us see this with a concrete example. We have a 2-year bond that pays a $100 coupon at the end of year 1 and a $1,100 total payment at the end of year 2. The current yield is 10%. We want to find the price change if the yield rises to 11%. First, we must find the present value of each cash flow to determine the total price of the bond. We discount the first year by 1 year and the second year by 2 years. Adding these gives a total bond price of exactly $1,000. Continuing with our calculation, we now find the time-weighted average using the Macaulay duration formula. We multiply year 1 by its present value of $90.91. Then we multiply year 2 by its present value of $909.09. Notice how heavy the weighting is in year 2, showing where the bulk of the bond's value lies. We add these together and divide by the total price of $1,000. This gives us a Macaulay duration of 1.909 years. The first year coupon pulls the average time slightly forward from 2 years. Finally, we convert our time metric into a measure of risk. We take our Macaulay duration of 1.909 years and divide it by 1 plus the current yield of 10%. This gives a modified duration of 1.735. This number is a direct multiplier for interest rate risk. To find the dollar impact of a 1% increase in yield, we multiply the negative original price of $1,000 by our modified duration and then by the yield change of 0.01. The calculation reveals an estimated price drop of $17.35. Now that we have used this formula, let us understand where it comes from. To find how price changes with yield, we take the first derivative of the price equation with respect to the yield y. We start with the standard present value summation for the bond price. Using the power rule from calculus, we move the exponent down. The negative sign appears because the denominator's exponent increases, perfectly capturing the inverse relationship between price and yield. This step forms the mathematical foundation for measuring price sensitivity, setting us up to connect this derivative back to our duration concept. Continuing our derivation, we will now simplify the expression to reveal a beautiful connection. We factor out a -1 and a factor of 1 plus y from the denominator. This isolates the remaining summation term on the right side. If you look closely, this isolated summation is exactly equal to the Macaulay duration multiplied by the total price P. By substituting this in, we connect the concept of time with the concept of price sensitivity. We are left with a clean, compact algebraic expression, showing that the derivative of price with respect to yield is -P times d over 1 plus y. Duration is a fantastic tool, but it has a fundamental flaw. It assumes the relationship between bond prices and interest rates is a perfectly straight line. In reality, this relationship is a curve. Because the true price-yield curve bends upwards like a smile, a straight-line estimate will always underestimate the true price of the bond when interest rates change by a large amount. Think of duration as driving a car with the steering wheel locked straight. It works for a few feet, but if the road curves, you will crash. Convexity is the act of turning the steering wheel to follow the curve. Let us visualize this flaw to understand it better. On this graph, we have the interest rate yield on the horizontal axis and the bond price on the vertical axis. The downward sloping curve represents the true bond price. Notice how it bends upwards. The straight line tangent to the curve is our duration estimate. As you move away from the center, the straight line falls further and further below the true curve. The vertical arrows labeled convexity arrow show exactly what duration misses. The straight line always underestimates the true price, which is why we need a correction factor. To fix this straight line error, we introduce a mathematical correction using convexity. If modified duration is based on the first derivative, convexity is based on the second derivative. We use a Taylor series expansion to improve our price change formula. The first term on the right is the standard linear modified duration effect we already know. The second term is the convexity adjustment. It adds a positive correction based on the convexity C and the square of the yield change. Because the yield change is squared, this correction always pushes the estimated price higher, perfectly fixing the straight line error. Let us see how this correction works in a real scenario. We have a bond with a price of $1,000, a modified duration of 5, and a convexity of 30. The central bank suddenly raises interest rates by a massive 2%. We begin by calculating the naive price change using only the modified duration. We multiply the negative original price by the duration of 5 and the yield shock of 0.02. This linear formula predicts a severe price drop of $100. But because the yield shock is so large, this straight line estimate is highly inaccurate. Now we calculate the convexity adjustment to fix our inaccurate linear estimate. We multiply 1/2 by the original bond price of $1,000, then by the given convexity value of 30. Finally, we multiply by the square of the 2% yield change. Squaring 0.02 gives us a very small decimal of 0.0004. Multiplying the first three numbers gives 15,000. When we multiply 15,000 by 0.0004, we get exactly $6. This positive number means the curve of the bond bent upwards, saving the investor from losses. Finally, we combine both effects to find the true price. We take the estimated $100 linear loss and add the $6 convexity correction back to it. This results in a true estimated price drop of only $94. The curvature of the bond acted as a shock absorber against the rising interest rates. Subtracting this drop from the original $1,000 gives a highly accurate new bond price of $906. If we had only used duration, we would have undervalued the bond by $6, proving why convexity is absolutely essential. We have covered a lot of ground today, so let us review the most important ideas. Macaulay duration finds the time-weighted center of a bond's cash flows, telling you the true average time to get your money back. Modified duration translates that time into price sensitivity, but it assumes a straight-line relationship. Because this becomes inaccurate for large interest rate swings, convexity measures the true curvature of the bond's price, acting as a crucial correction factor. Together, these two metrics allow banks and investors to accurately predict bond prices, immunize their portfolios, and protect their wealth from unpredictable economic shifts.